Okay, this lesson is on area under a curve, and this is my introductory lesson after we have finished derivatives. So the first situation that we just want to talk about is a train moves along a track at a steady rate of 80 miles per hour from 9 a.m. to 12 noon. What distance did the train travel? And so this presents some questions, and I just want you to take a minute and see what you would get, how you think about it. Okay, so one of the first things that typically comes to everybody's mind is just multiplying the 3 hours that passed times the 80 miles per hour to get that total. What you're really doing when you do that is using this formula, distance equals rate times time, which I'm sure you've come across in other math or science classes. And so you are taking the rate, which is 80 miles per hour, and multiplying it by the 3 hours that pass between 9 a.m. and 12 noon. And you do get 240 miles in that case. I do want you to notice something that you probably haven't thought about before, and that is that the hours is on the bottom of the fraction here when you're talking about the units, and it's like basically on top, so to speak, here. And so the hours actually do cancel out. They work just like the numbers, and that's how you end up with just having miles in your answer. And again, the 80 times 3 gave you the 240. Okay, now I want you to think about that another way. I want you to think about what the graph of that would look like. So I want us to just create a little axis. We're going to graph the velocity or the rate on the y-axis and the time on the x-axis, and we're just doing basic. Our times that are important are 9 and 12. I'm not getting real specific with my labels here. And the velocity that's important to us is 80 miles per hour. What kind of graph would this look like? What would this shape be? So it would be flat because this shape, the rate is 80 miles per hour the whole time. It stays exactly the same. Okay, now I want you to notice something. Think about the area under that line and between the 9 and the 12. So kind of imagine a little rectangle here. Okay, I want you to calculate the area of that rectangle. So area of a rectangle is length times width. Our length is, our base here is 9 to 12, which is 3. Our width or our height is the 80. And notice that that gives me 240. So it's giving me that same output that I got from the formula distance equals rate times time. This is an important thing to realize because this is going to be how we relate many things in the coming units. I specifically want to talk about the relationship between distance, velocity, and acceleration that we talked about before. We looked at velocity as the derivative of a distance equation, and distance, again, we normally used an S instead of a D, and then the derivative of the velocity was acceleration. So what we're talking about here is we were given a velocity. We were given that rate, and we actually went backwards using this algebra formula or using this area to find a distance. So we went backwards from the calculus relationship that we had talked about before. And so when you go backwards, you're actually calculating area between that curve and the x-axis, or area under the curve, hence the title of the notes. Okay, so that was a basic example. Now let's change the problem. Still having our train moving on the track, but we're going to say that from 9 a.m. to 10 a.m. they were going 20 miles an hour. From 10 a.m. to 12 p.m. they were increasing linearly their speed from 20 miles an hour to 60 miles an hour, so very slowly increasing but linearly at the same rate throughout that 10 to 12 time period. And then from 12 to 2, they were going at a steady 60 miles per hour. So I'm just jotting down the basics for you here, but we're making the problem a little bit more complicated with these values. The question is still, what distance did the train travel? Okay, so this time we're going to use the graph and calculate the area to get the distance, since that's our new idea here. And that middle section would be kind of hard to do with our distance equals rate times time because the rate is changing. So doing a graph is going to be a bit easier to figure out that total answer. So this time, let's again put velocity on our y-axis and time on our x-axis. The velocities that matter are 20 miles per hour and 60 miles per hour. The times, I'm just going to label 9, 10, 11, 12, 1, 2. And yours will probably look a little bit better than mine. Now, I'm going to graph these. When they're going a constant rate, like from 9 to 10 or from 12 to 2, those are horizontal lines just like we dealt with a minute ago. So between 9 and 10, we are a flat line at 20 miles per hour. Between 12 and 2, we are a flat line at 60 miles per hour. The part from 10 to 12, they're increasing between the two linearly. So in other words, I'm going to connect those with a line that has a positive slope. And it should be a perfectly straight line. Obviously, sketching it, it's not quite that way. Okay, so now that we've got it drawn, to calculate the distance, we want to think about that area under that graph and above the x-axis. So all this little area in here. And that's not a nice geometric shape that we know. That is, you know, kind of a funky shape. But you can separate it into things that you do know. So I'm going to draw some little dotted lines right here and right here. Because these three shapes, when I look at them separately, are things I know. The first one is a rectangle, the last one's a rectangle, and the middle one is a trapezoid. It's just turned sideways from what you're probably used to looking at in your geometry studies. So, first, I'm going to do the area of this rectangle from 9 to 10. So the base is 1 and the height is 20. So 20 times 1 is 20. And I just kind of make notes in there. And then I'm going to go to the last one because it's easy as well. So from 12 to 2, that base is 2. But then the height, the y value goes up to 60. So 2 times 60, this area ends up to be 120. Now, the middle shape, like I said, is a trapezoid, and it is turned sideways. Your parallel sides are the two dotted ones, and the area formula for a trapezoid is 1/2 height, base 1 plus base 2. So I'm going to have to come over here and do a little bit of scratch work on that. My height is actually the distance between the two parallel bases, so it's actually 2. It's the 10 to 12. Your base 1 and base 2 are the two dotted lines, and so those are 20 and 60. And so if you, the 1/2 times 2 will just be 1, the 20 and 60 will give you 80, and so that middle section ends up to have an area of 80. So the total distance it traveled would just be 20 plus 80 plus 120. So 220 miles. Okay, so with this now we're going to learn a vocabulary word. The area that is trapped between the velocity graph and above the x-axis is now going to be known as the integral. So that's going to refer to that specific area. So new vocabulary word there. Okay, so now we're going to make the problem even more complicated. So not just geometry type formulas to figure out areas. So what if our velocity equation looked like t squared? So it looked like a parabola for t greater than 0, because obviously time's not going to be negative for our situations. How far did it travel over 0 to 4? From time 0 to time 4, obviously the first 4 hours, whatever that situation is. So let's look at that graph. If, again, I'm graphing velocity on my y-axis and time on my x-axis, to look at the graph of t squared for t greater than 0, that is half of a parabola, kind of looking like this. And so how far it traveled would be, looking for the area under here, and if you notice now what you're looking for, it is harder to deal with because this is not a straight geometric shape that we know an area formula for. And that is actually where calculus comes in. Finding that exact area, we use new techniques that we're going to be learning about to get that exact area. Okay, so if you think for a minute, how would you get an approximation for the area? What kinds of ways would you approximate? Obviously it wouldn't be exact, but just knowing geometry formulas, what would you use? Okay, so a lot of people say that this looks like a triangle, and they would use a triangle to approximate this, but since many of our functions have different shapes, this one, being the t-squared graph, happens to look similar to a triangle under there. Not every function that we use is going to have that shape. So the calculus creators, people who figured it out, the mathematicians who worked with calculus, they decided that they were going to use something that was easy to approximate area with for all of the shapes, so that there was a similar method throughout, no matter what the graph was shaped like. And that method was to use rectangles. Rectangles have a very easy area formula, base times height or length times width, and so it's simple math to do. So let's look at the first being a right-handed rectangle approximation of our problem. So let's draw our velocity graph again. Okay, so here is my velocity graph. We know it was for 4 hours and it resembled the shape of t squared. A right-hand rectangle approximation means the right-hand side of the top of the triangle, the top of the rectangle is touching the function. So I could do different amounts of rectangles here. I'm going to do 4 because we had 4 hours, and that's just a nice, easy way to look at it. So between time 0 and time 1, I'm going to draw a rectangle that approximates this area and touches on the right-hand side. So touches the function at 1. Between 1 and 2, I'm going to draw one that touches at 2. And between 2 and 3, I'm going to draw one that touches at 3. And sometimes it's easier if you go up from that particular x value where it's going to touch. And then from 3 to 4, I'm going to do one that touches on the side where the 4 is. Now, obviously, these are not a great approximation of the area. We have more area under all of the rectangles if we added them together than we have under the graph of t squared. But the key word there is approximation. This is close to, but not exact, for the area. So we're going to calculate this area that is in these rectangles, and in order to do that we need to know what those heights are. You get those from your equation, which was velocity equals t squared. So whatever that y value is, it comes from squaring the x value. So the first one, it touches the function where the x value is 1. So 1 squared is 1. That means that the height of the first rectangle is 1. The second rectangle touches where the x value is 2, so 2 squared being 4 means the height at the second rectangle is 4. The third one touches where the x value is 3. 3 squared is 9, so that height is 9. And then the last one touches when the x value is 4, so 4 squared is 16. That y value is 16. Now, technically, this is what you're looking at. When I'm doing these problems where they're asking me to do these area approximations, I tend to write the y values on top of the rectangles as kind of a shorthand way so that I don't get confused about what I'm doing. So if you see me doing that, those are the y values. They go on the y-axis, but because we're figuring this out, I'm going to go ahead and make it easier for myself to think about, and you can do that too if it helps you. So let's calculate this approximation. I'm going to say this right-hand sum, this right-hand approximation. The first one, 1 times 1. The second one, the base is 1, the height is 4. The third one, the base is 1, the height is 9. And the last one, the base is 1, the height is 16. So 1, 16. And so if I added all of those up, I'm going to get 30. So this train would have traveled 30 miles with that type of a setup. And again, a lot of times with these, they'll ask you whether this is an overestimate or an underestimate. And since I had more area under the rectangles than I had under my graph, I would classify this as an overestimate if I was asked. Okay? Now, I want you to think for a second about what we did and tell me what could have made that better. Still using rectangles, still using right-handed rectangles. How could I get a better approximation for that area? Okay, so it turns out that a way to get a better right-handed rectangle approximation would be to have more rectangles. So let's erase what we have here, or you can write down another version of this, and let's do some more rectangles here. Okay, so I'm starting with a clean graph here. The way to make more rectangles is to make the base of them smaller. In that first one, we chose just a base of 1 because it worked nicely with our hours. So let's say that we looked at every half hour. So we're going to look at an x value of 1/2, an x value of 3/2, and it's easier, in my opinion, to keep these as top-heavy fractions to figure these out. This would be 5/2 and 7/2. So I'm going to go ahead and draw in the rectangles at each of those locations. Okay, for some reason I keep losing this first one, but we'll come back to it in a second. I've already done the math for the ones at 1, 2, 3, and 4, so I know the height of the one that touches at 1 is 1, the height of the one at 2 is 4, the height of the one at 3 is 9, and the height of the one at 4 is 16. And like I said, that's how I do my shorthand, is by writing them on top. For this first one that does not like me, you're plugging in 1/2, and the reason I said to keep it as a fraction is just easier when I'm squaring the fractions to square the top and square the bottom and just think about it that way. So 1/2 squared would be 1 squared over 4, or 2 squared, which would be 1/4. Then 3/2 squared would be 9/4. 5/2 squared would be 25/4. And 7/2 squared would be 49/4. And so I can get those pretty quickly just thinking about the tops and the bottoms separately. Okay, so this is an overestimate, but obviously look at the little what's left out. You're getting closer and closer to that exact area because you have less area over the function than you had before. It's still an overestimate, but let's figure out what our right-hand sum or approximation for that distance would be. So I would do my base. Now my base is 1/2 because each one of those will be 1/2 wide, times the height, which will be the y value in each case. So the first one would be 1/4. The second one would be 1/2 times 1. The third one would be 1/2 times 9/4. Then I'm going to have 1/2 times 4. 1/2 times 25 over 9, 1/2 times 9, 1/2 times 49 over 4, and finally 1/2 times 16. I could have written that, like, factored a 1/2 out, like a GCF, and put 1/2 and then put all of those just added together. I'll show you that just to let you keep that in mind. It's less to write down. So it's just factoring that out like a GCF. And that is allowed. So you could write it like this. Either way, you're going to get the same answer. That answer happens to be 25.5. And since we're talking about a distance in miles, I'm going to put those units on it. And obviously that's less than 30. It's still, we know, an overestimate just based on the look of it, but it is closer to the actual value. Now, obviously what we just did gave us overestimates. We're going to look at the left-hand rectangle approximation now, which means the left top corner of the rectangle is going to touch the function. I'm going to use that same function, so let's take a minute to draw it in. Okay, so again, left hand's going to touch on the left side. So between 0 and 1, that left side is at 0, so that one is actually flat. It has 0 height. But between 1 and 2, it's going to touch on the side where the x value is 1. Between 2 and 3, it's going to touch on the side where the x value is 2. And between 3 and 4, it's going to touch on the side where the x value is 3. Obviously, in this case, it's an underestimate. You don't get all that area covered by rectangles, but again, it's fairly close to what it should be. And if we made more rectangles like we did in the last problem, we would get closer to the exact value. So let's calculate this value while we're here. Again, the first one is flat, so its y value is 0. The second one, the height comes from the 1, so 1 squared would be 1. The next one, the height comes from the 2, 2 squared would be 4, and then the last one, 3 squared, is 9. So if I'm doing a left-hand sum, my first one would be 1 times 0. My second one would be 1 times 1. My third one would be 1 times 4. And my fourth one would be 1 times 9. And again, I could have written the height and then added written the width and then added all the heights up like it was a GCF, which is fine. Obviously, this is going to be 0. I end up adding everything up and I get 14. So we know it's less than 30, more than 14, or less than 25.5, more than 14. It's somewhere in there. We are going to be looking at specifics on, turning this into getting the exact values in a future lesson, but it does have to do with making more and more rectangles. If I had made the width of each one 1/4 instead of 1/2, I would get even closer to the exact area. And then if I would go even smaller than that, even 1/100th, if I could make the width that and do all of that math, I would be closer and closer to the exact area, although I would not be exact. Okay, I do want to point out today that all right-hand sums are not overestimates. Okay, so for example, if I had a different graph, if I had one that looked maybe like this, and I did right-hand sums on it, I would actually have an underestimate here because this area would not cover all of the area that I would be looking for. So just because it's right-handed doesn't mean it's an overestimate, and in that same thought, just because it's left-handed, so all left-handed sums are not underestimates. I mean, if I did that same graph or that same shaped graph and I did a left-handed sum, the left-handed side would be an overestimate in that case. So don't connect what side it is with being an overestimate or an underestimate. Okay, that is based on whether those rectangles go outside or inside of your shape. And again, I'll give you some more information on that later. We're just going to start with calculating these right and left hand sums for some different shapes with this lesson. And that concludes this lesson for today.